I continue to tell you something about techniques for site characterization of groundwater heat pump systems in our part 2. So in the last part, in the part 1, actually, we defined already that we need to define the volume, what can be extracted from the groundwater, to define also how much energy or how much heat can we use from the underground. So in the part 2, we said, okay, groundwater thickness and hydraulic gradient are important, and we got to know how to measure that. And now we will talk about the hydraulic conductivity. So hydraulic conductivity is defined by how much water can flow through my rock, and this is strongly dependent on the porosity. But not all porosity in a rock can be used by the water to flow through, so we talk about the efficient porosity. And there is a big relationship between the efficient porosity and the hydraulic conductivity. So how much water can flow through my rock depends quite a lot on the grain size of our rock. So the grain size distribution, especially in unconsolidated rocks. So if we have a larger grain size, and this is quite very clean, so there's not a mixture between other grain sizes, then we have a higher porosity and also higher hydraulic conductivity in general. So if the grain size goes down, normally also the hydraulic conductivity goes down. So by clay sediments or silty sediments, you have in general lower hydraulic conductivity. But of course, also a mixture can be caused then lower hydraulic conductivity. Hydraulic conductivity is measured in meter per second in general. Of course, you can use also Darcy as a unit. In consolidated rocks, so normally hot rocks, you have also differentiation in the hydraulic conductivity, of course. There, the hydraulic conductivity is mainly caused by fractures, karstification. Of course, you can also have matrix porosity, but in general, also karstification and fractures, as I said, are very important. Of course, how can we assess now what is the real hydraulic conductivity? Of course, you can use, if you know the lithology of your aquifer, use literature values, but there are just very rough averages, so you have to know the real conditions at your place. So we do a pumping test. So what we do is we abstract water, which is named here by Q, and then we see if we abstract water, the water table is decreasing at our location. And this is then we have a so-called drawdown curve. So what we measure normally is, as I said, the volume which we pump out, and then what is the drawdown over time, so the small s value here. Of course, you can use single well tests, so just one well, but you can also use observation wells for the calculation of the hydraulic conductivity. And then you measure here also the drawdown, and then you make the relationship between the radius, which is where the observation well is away from your single well, and the drawdown, and then you can also calculate the hydraulic conductivity out of it. Of course, you have also to see what conditions do you have. So do you have a confined or unconfined aquifer? This makes a difference. And we talk a lot also about transmissivity, and not only hydraulic conductivity. The transmissivity is hydraulic conductivity multiplied with the aquifer thickness. So if you calculate also transmissivity, you can then calculate also the hydraulic conductivity if you know the aquifer thickness. Of course, in general, if you pump out a specific amount and a constant volume, then if you have a higher hydraulic conductivity, then the drawdown is lower. If you have a lower hydraulic conductivity, you create a larger drawdown. That's in general the effect, what we are using. So for the interpretation of pumping well tests, of course, we use, as I said, then the so-called pressure curve or drawdown curve. So we draw here for a specific pumping rate, then the drawdown over time. And you see on the left side, of course, over time, if you start then actually your drawdown develops until it reaches a static level. So that is then with a specific pumping rate you are operating, then actually the drawdown is stable, which means the same amount of water what you pump out is actually then flow through your well, and so you get a stable conditions there. And so by this relationship between drawdown time and stable drawdown and also the pumping rate, we can calculate actually then our hydraulic conductivity. This is a Theis equation, so you don't have to go in detail here. But with this equation, actually, there is the relationship between transmissivity and drawdown, and also what is important is the storativity. So how much water can be stored or is stored in the underground. This is also a value what you have to know. So, and with these values, you try to fit then some curves by a superposition methodology. So you have your measured parameter and you try to fit it to the theoretically well curve here from Theis, for example. So how does it work? So you have your drawdown values and the values you measured, and then you try to fit it or here on a semi-logarithmic diagram, you fit it to some theoretical curves, and by fitting it with the parameters of Q, your pumping rate, the abstraction rate over time, and also the storativity value, you can assess the transmissivity, and if you know the aquifer thickness, which you measure, then you can calculate the hydraulic conductivity out of it. Of course, for several conditions, confined, transient, if you use actually the transient part of your drawdown curve or the stable part, there are several methodologies, several analytical methodologies to derive then your hydraulic conductivity. So here you have a list of a few ones for specific conditions. There is continued here. So if you have confined or also leaky confined conditions, if you have unconfined conditions, and so several methodologies which can be used then to derive the hydraulic conductivity. So this is what you usually do. And of course, having the hydraulic conductivity, the groundwater thickness and hydraulic gradient, which we got to know in the part 1, then you can calculate a technical volume or the abstraction rate. So you can calculate how much water can I pump out. Of course, also the well which is used, so the well diameter and also some losses which must be calculated from the technical design of your well are important. But in general, you can then assess with these parameters how much water can I pump out. And here you see we did that once for the Munich example case here. And you see if we have a higher volume of water and higher hydraulic conductivity, then you can pump out a lot more water on a specific place. And if you have a lower amount of water, groundwater available, of course, you have a less potential to pump out here a specific amount of water. With this information, of course, coming back to the heat, then of course you can calculate how much heat can be extracted from the underground, from the groundwater at a specific point. Of course, if you then you have to define then how much temperature do I use. For example, if you use a heat pump and temperature spreading of 5 Kelvin, then you can say with my technical volume rate what I can abstract from the underground, and temperature spreading of 5 Kelvin, for example, this is used here in this example, we can calculate what can we abstract, how many heat can we abstract at a specific point, what you see here. There are some specific issues what you have to consider as well, and this will I will explain it in the next part 3.